Greetings and welcome to Dr. Lisa's Quick and Dirty Guide to the T-Test Part 2. We began by sort of laying the groundwork, at least somewhat, in the first video, and for this one we're going to actually get to the test. We're going to actually get to the numbers, since I was kind of teasing you before. The test itself is going to look a little scary. There's formulas. They are not nearly as scary as they look. Trust me on this, okay? Once you know what all these things are, a lot of this, like I said, is just plugging in numbers. Very often the hardest part of statistics is figuring out what test to use. It isn't necessarily doing the test. So, this is Chapter 8. In a single sample mean test, we're comparing the sample mean to the population mean. We want to see if that sample that you have pulled out of the population and presumably done something to. We're going to see if that sample that you have collected, whether you've done something or not, is the same as the population mean. Remember we were talking about that the hybrid mileage is assumed to be 50, and so you take a sample and you want to see if your sample, well, we're going to compare the mean of those sample hybrids that you pulled out to the population mean, which we're assuming is 50 miles per gallon. And we want to then see if our sample mean is the same as 50 miles per gallon, is plus or minus 50 miles per gallon, and how much. Because if it's only a little bit, it could just be chance. And the point of this is to figure out whether the difference is significant or whether it's not. We need to separate a significant difference from sample error. Maybe you picked out a couple of bum cars. Maybe those cars didn't get adjusted correctly. Maybe they were over-adjusted. Maybe you got a bad tanks of gas. Maybe it was a windy day. Maybe you were going up a hill. Trust me, I own a hybrid. They don't go up hills very nicely. And when they go into the wind, you can watch the gas gauge go down. And yes, I have actually gone up a hill into the wind, and trust me, it ain't pretty. So we need to see whether or not that difference was significant or whether it simply was an error. So the first thing we're going to do, remember with t-tests, we don't necessarily know what the population standard deviation is, or the population mean for that matter, because we don't know what it is. So we're basically going to assume that the mean of all of these possible samples that we have is the same as mu. Which is basically my way of saying, yes, in a t-test we're going to use mu when we should only be using it in a z-test, but trust me, we kind of know what we're doing. Welcome to math and psychology. Next, you're going to compare your samples mean. You're going to compare those hybrid cars you pulled out of the population to assume the mean to the assumed mean of the sampling distribution of sample means. Trust me, it's easier to not have to read this out loud, i.e. the population mean. What you think the population mean is, and calculate the difference. What's the difference between the average of those cars that you pulled out of that particular group and the entire group? Is there a difference? Is that difference real? And then we're going to basically put the differences into standard error units, which is simple. You divide it by the standard error, which you already have figured out at some point. And then you look it up on the chart. And yes, there is a chart that you're going to need to print out or have handy when you take the test, because you're going to need to look some of these up. The formulas, like I said, these are a little scary. Don't be frightened. Take a deep breath. When we know the population standard deviation, we usually use a z-score. Now, as I said, you may have used a z-score back in descriptive statistics. You may not have. It's a fairly simple thing. You take x bar, which is the sample mean, you subtract the population mean from it to get the difference, and then you divide it by the standard deviation of your sample. How do you find the standard deviation of your sample? That's what the sigma over x bar is. You take the standard deviation of the population and you divide it by the square root of the number of items in your sample. N is number, virtually always, okay? And that's a square root. So if you had 10 items in your sample, if you had 10 cars, then basically the sample standard deviation there, the sigma x sub x bar would be equivalent to 50 Assume we don't know what the population standard. And anyway, it would be equal to the standard deviation divided by the square root of 10. When we don't know the population standard deviation, which is almost always, we use this, which, glory be, looks pretty much exactly like the z-score, the z-test, except it has slightly different letters here. So we still have x bar, we still have the mean of your sample, and we still have mu, which we're kind of assuming is the population standard, or population average or mean or something similar. Hint, you'll probably be given a lot of these numbers, both on the test and in your homework, divided by the standard deviation of that particular sample mean, which is equivalent to the standard deviation of the sample divided by the square root of n once again. They're essentially the same formulas, and a fairly simple one at that. You figure out the standard deviation sub x bar, whichever one it is, whether it's sigma or whether it's s, and then you just plug your numbers in and it gives you a t-score. And once you get that t-score, you go look it up on the chart. Once you've decided what the level of significance is, the level of significance is almost always 0.05. That says that there is a 5% chance that this score is due to chance. Only 5% of the time would a score this extreme be due to chance. And that is generally what we use in terms of picking our alpha level, which you hopefully got from chapter 7. And that's basically it. You plug in numbers, you look it up on the chart, and there you are. So here, let's run through a couple on here. Again, feel free to pause this and write stuff down. The mean SAT scores of senior students attending Bedford Senior High School has been 550. This is, for a while there, they actually took SAT scores out of 2,400. Now they're back to only doing it out of 1,600. So let's say that it's 550. We're going to call that like a math score or something, because if that's the entire score, that ain't very good. I think you get a score of like 200 for filling out your name. At any rate, a random sample of 72 seniors finds a mean score of 574. Ooh, 574, so it's 24 units higher. Assume that the population density, notice how it's saying that. Like I said, in a lot of ways, they're going to give you the numbers. Assume that the population standard deviation is sigma equals 100. Okay? Is this year's average significantly different? Well, what do? The first thing you need to do is sit down and figure out, okay, what is the standard deviation of the mean? Well, okay. First, you do the null hypothesis. So the null hypothesis is that the mean of the sample and the mean is the same as the mean of the population. That's what we're talking about. So we're picking a critical value. We're going to use 0.05. If you look 0.05 up on the t-chart for what's called a two-tailed test. Now the difference between one-tailed and two-tailed is, with a one-tailed test, you're only looking to see if it's bigger, or you're only looking to see if it's smaller. So it's only one end. A two-tailed test means you're looking to see if it's bigger or smaller. You don't care. And so therefore, a two-tailed test in the table for the z-score is 1.96, plus or minus. Because again, we don't know whether it's just going to be bigger or smaller. We just want to see if it's different. Notice up here where the null hypothesis is. The alternate hypothesis is that it's not 550. It doesn't say it's bigger or smaller. In that case, you'd use a different number. Calculate the test statistics. Okay, here we go. We have the numbers for this. We have the population standard deviation, which is 100. We have the n, which is 72. So we have 100 divided by the square root of 72. So we have 11.7851. Use at least two numbers past the decimal point, unless I signify otherwise on the test. It's quite possible that if you use more or fewer digits beyond the decimal point, that your answer that you get is going to be slightly different than the answer that is available on this multiple choice test. Pick the closest answer. How's that for a hint on how to do well? Pick the closest answer. And now that we have that, we plug in the rest of the numbers. What's the z-score? We have x bar, 574. That's the average of our sample. We have the population average, which is 550. We have the standard deviation of the sample, which is 11.785. So you figure it out, you wind up with 2.03647, which indeed is more extreme than 1.96, which means what do? We reject the null. This is more extreme. This is so extreme that it would happen even less often than 5% of the time by chance. So we're accepting it. Does this mean that this is absolutely positively true? No. Because it's always possible. 5% of the time, it's going to just be chance. But we figure that that's a pretty good bargain. 5%. Sometimes people do the 99%. So it's only 1%. But that's going to be a lot harder to get. You're going to get that, make that significant a lot less often because you're going to miss some things that you're going to be more likely to make one of those lovely errors. It's all about balancing the type 1 and type 2 error. How about a single sample test where we don't know the population standard deviation? 12 gas stations randomly sampled. Price of low grade was $3.32 a gallon. It was expensive. With a standard deviation of 0.6. So we looked at 12 gas stations. Okay. Furthermore, a normal indicates the data is consistent with having come from a normal population. Okay. So we basically want to see, we're going to compare that sample you pulled to the 4 weeks average of $3.35 a gallon. Okay. This is 332. The average is 335. Is the 332 significantly different with a standard deviation of 0.06 cents per gallon? Let's look. Formulate the null. Again, the null hypothesis is there is no difference. The alternate is that there is. It could be higher or lower, we don't care. Therefore, we're picking the critical value. Now, when you're doing a t-test, you have degrees of freedom. It's a little trickier, okay? Degrees of freedom are basically n minus 1. And when you look at the t-test, you'll see a line that says degrees of freedom along one axis, and then along the other axis, you'll have whether it's 0.05, whether it's one-tailed or two-tailed, and so forth. So your book goes into how to track these down. But trust me, a 0.05 with a degree of freedom of 11, where it's two-tailed, it's going to be 2.201 plus or minus. Now, you don't have to memorize this one because this is going to vary depending on your degree of freedom. Calculate the test statistics. Okay, plug in those numbers. So here we go. We know what S is. We know what a standard deviation of our samples is. It's 0.06. We know what N is. It's 12. Bingo, 0.0173. So plug those in with the population mean, with the sample mean, and we get a difference of minus 1.7341, which is less extreme than minus 2.201. Since it's less extreme, we're going to accept the null, or we fail to reject it. The way that's phrased is very, very precise. You can't really prove a negative in science. You can fail to support it, but you can't prove it. So we simply said we failed to reject it. So in other words, in non-science words, there's no difference. Which you probably figured out looking at it. I mean, it's not very impressive. So this is what you're going to need to be able to do basically for Chapter 8. And I'll get to Chapter 9 in the next video. But guess what? Chapter 9 is going to look a heck of a lot like this.